Alright, so now we're looking at a group question. A light ray with a frequency of 5.09 times 10 to the 14 hertz traveling in water has an angle of incidence of 35 degrees on a water-air interface. At the interface, part of the ray is reflected and part of the ray is refracted. So, let's look through this. 76, what is the angle of reflection of the light ray at the interface? One of the keys here, angle of reflection. Now, law of reflection, this is an equation in your reference table. It says that the angle of incidence will be equal to the angle of reflection. And so if the angle of incidence is 35 degrees, the answer for 76 is also 35 degrees. And that'll be it. For 77, on the diagram in your answer booklet, using a protractor and straight edge, draw the reflected ray. So now we're going to have to draw this angle of 35 degrees, so I'm going to pull up my protractor real quick. So we have a protractor out, and we need to draw the angle of reflection from the straight edge. Now one thing to point out here is that this right here is our boundary. And so the reflected ray is going to bounce off the boundary and stay on the same side of that boundary as it started on. And so the reflected light ray is going to be somewhere in this direction. But remember, it's asking us to measure that one out. So we take our protractor, we center it right along that line. And one thing to remember here is that we measure all of our angles from the normal. So when we rotate our protractor, we're measuring from the normal, which means that we need to put it sideways like this. We start here at the normal. We're going 35 degrees away, which brings us, right, figure 10, 20, 35 degrees away, right here. And when you draw your line, So when you draw your line, we remove our protractor, start here, and that's going to be all right. And our angle of reflection is this guy right here, 35 degrees. So we're all set. We can get rid of our protractor now. Now, some of the light gets refracted, and some of it gets reflected. So now we want to look at the light that got refracted, the light that did pass through this barrier. We want to calculate the angle of refraction as it enters the air. So refraction, we can calculate the angle of refraction using Snell's law. That's the equation that n1 sine theta 1 is equal to n2 sine theta 2. So the 1s, or our first side, will be where we started, which is in water. You'll need to look up the index of refraction for water. Now this one's in your reference tables, and when you look it up, it should have a value of 1.33 times sine of, but we started the incident angle is 35 degrees, is equal to n2. Now n2, you also have to look this one up. The n value for air, the index of refraction is 1 times sine of theta 2. A little bit of algebra will get you to this point. 0.76 is equal to sine of theta 2. And the last thing to do here is to get rid of that sine. You need to do the inverse sine. That's the sine to the -1 button on your calculator. When you do that, you get an answer of 49.7 degrees. And that is our answer to 7879, which leaves one more to go. 80. Identify one characteristic of the light ray that is the same in both air and water. Now, as the wave changes medium, one of the things to know here is that anytime you have this transmission or change in medium, the frequency will stay the same. And so an acceptable response for 80 is frequency. Also acceptable would be period. Because period depends strictly on frequency, right? That's the equation, period equals 1 over the frequency. If frequency stays the same, then another thing that stays the same would be the color of the light. And you think about it, if you look at an object that's under, some water, it doesn't change color as a result of that. And so the electromagnetic waves would not be changing the color. So you have a few different responses that you could use there for number 80. All of them would be acceptable.